This is Unit 1, Lesson 2, Transformations of Functions. So again, here's my textbook. My lesson essential question today is, what do the differences between the equation of a function and the equation of its parent function tell you about the differences in the graphs of the two functions? Okay, so my vocabulary today is compression, reflection, stretch, transformation, and translation. And by the end of this lesson, I can apply transformation to graph functions and write equations. All right, so explore and reason. The graph of the function f of x equals the absolute value of x is shown. So here's my graph right here. So this is an absolute value function graph. It makes a V shape as opposed to a U shape, which is a parabola, okay? So I want to use the tool to graph the function g of x equals x plus c several times with different values for c, any value from -5 to 5. Okay, so I'm going to go ahead and click here. I'm going to do g of x equals absolute value of x plus 2. Okay. G of x equals x minus 2. G of x equals x minus 5. G of x equals x plus 3. Okay, so I've graphed a couple of the functions, and you can notice they're still all V shapes. They're still the same shape, but all I've done is I've just moved the points to different spots on the graph, on the x-axis. Okay, so x plus 2 is the first one I graphed. It just moved over to -2. X minus 2 on the graph moved over to +2. X minus 5 moved over to +5. That's my green function. X plus 3 moved to -3. Okay, so looking for relationships. Predict what will happen to the graph if c is a number greater than 100. What if c is a number between 0 and 1/2? All right, so if c is greater than 100, what's going to happen? All that's going to happen, so if c is greater than 100, the graph will move toward the negative numbers. Okay. So we'll just move towards negative numbers. So they're just shifting from left to right. All right, what if c is a number between 0 and 1/2? Okay, so we'll just see a very large horizontal shift, or for c is between 0 and 1/2, you're just going to see a very small horizontal shift to the right, because it's going to be, I'm sorry, to the left, because it's still between 0 and 1/2, so it's positive, so it's going to shift to the left. Okay. So habits of mind. What happens to the graph if c is a negative number? Okay, so remember, it's still absolute value. So if c is a negative number, we still will have a shift, either a horizontal shift to the left or the right, depending on how large the negative number is. Okay. It's more likely going to go to the right. So shift to the right, depending on how large the negative number is. All right, example number 1, translate a function. Graph the function f of x equals x squared for the domain -2, 2. Remember, we had brackets. Brackets means that includes the -2 and the 2. The graph of g is obtained from the graph of f with a transformation 3 units down. How are the equations, domains, and ranges of f and g related? Okay. So the first thing that we want to do is actually graph both of these functions. the slider to compare a point along the graph f and g. So here's my first point, x squared for the domain negative 2, 2, and the graph g is obtained from the graph f with a transformation 3 units down. So here's my original function from negative 2 to 2, so that's why the dots are here. So negative 2 to 2, and all I did with g was I just moved it down 3. So you can see negative 2, I went negative 2, 4. From this point, I went down 3, 1, 2, 3, and that's how I got my new point. On this side, I went down 3. On this side, from the bottom, I went down 3 as well. Okay. So every point on the graph G is 3 units below a corresponding point on the graph of F. So f of x is x moves to x f of x minus 3, and that gives me x g of x. So g of x equals f of x minus 3. So any point on that graph that I'm given, minus 3, will give me g of x. So the domains of f and g are the same, still negative 2, so the domain, remember, is our x. Okay. Our range values are going to change. The range values of g are 3 units less than the range values of x, or f. So f here, we start at 4. 4 is the highest it goes, and 0 is the lowest it goes. So that's my range for f, highest to lowest. Same for g. My highest point is 1. My lowest point is negative 1, 2, 3, negative 3. So negative 3, 1, because that's my x and then y. Okay? So range, negative 3 to 1, that's the range. And then the domain state are the same. So a translation like this one in particular, like this one is a particular kind of transformation of a function. It's one that shifts each point on the graph the same distance and directions. Other kinds of transformations of a function can reflect the graph across the x-axis, across the y-axis, or stretch the graph, stretch it this way, stretch it this way, or they can compress the graph, or depending, okay? So in general, if g of x equals f of x plus k, then the graph of g is a vertical translation of the graph of f by k units. So just like we did up here, this k is just any number that's where you're translating it. Either it's going up or it's going down, depending on if this is a positive or a negative, okay? So let's look at B. B says graph the function f of x equals x squared for the domain negative 2, 2. The graph of the function g is obtained from the graph of f with a translation 3 units to the right. How are the equations, domains, and ranges of f and g related? Okay, so I'm going 3 units to the right. Okay, so I still have the exact same graph, but I'm going 3 units to the right. Okay, so here's my original graph. It looks the exact same as the one we just looked at. Okay, it's the same exact graph from negative 2 to 2. Okay, and all I did with this graph is I just moved it over. Moved it over, 3 units to the right. So every point on the graph G is 3 units to the right of the corresponding point. Okay, so that means, so here's my domain is negative 2 to 2. My domain for this graph is going to change because I moved it over. I moved it, it was a horizontal shift instead of a vertical shift. So my new domain is 1 to 5. 1 to 5. Okay, so there's my domain. My range, so they're still the same, 0 and up. In this case, 0 to 4. But if it were just the function, it would go all the way to infinity. Same with this one, 0 to 4. Oops. 0 to 4. Okay, or 0 to infinity. It would continue on. Okay? So in general, g of x equals f times the quantity x minus h. So I'm going to take whatever my x value is plus 3. That's why it's a horizontal shift as opposed to a vertical shift. So there is a difference. So a vertical shift is g is f of x plus k, a horizontal shift is g of is f of x minus h or k, or whatever you would like to use for that. Okay? So I take my function and then I subtract 3 from each point. In this case, I take x and I subtract h from it. So then the graph of g is a horizontal translation of the graph of f by h units. All right, there is a try it problem. So it says, how did the transformation of f of x equals x squared to g of x equals x squared minus 3 in part A affect the intercepts? Okay, so I'm looking at where it crosses the y-axis or where it crosses the x-axis. So looking at the y-axis, so it affects the intercepts right here. So for f of x crosses at the origin, g of x crosses the y-axis at -3, so it shifted 3 units down. For the x-axis, f of x crosses the origin, and g of x crosses the x-axis between -1 and -2 and 1 and 2. We don't know that exact point without doing some other math for that. So we can check our answer. From f to g, the y-intercept is translated down 3 units. F had 1 x-intercept at the origin, and g has 2 intercepts on either side of the origin. Okay. 1b, how did the transformation of f of x equals x squared to g of x equals x minus 3 squared in part B affect the intercepts? So looking at this, f of x crosses at the origin, while g of x touches the x-axis at 3, positive 3. There is no change crossing the y-axis in this graph. However, if you if you extend g of x further, it will cross the y-axis one time, right over here on this side. All right, example number 2, reflect a function across the x or y axis. So graph f of x equals 2x minus 6, and the function g is a reflection of the graph of y across the x-axis. So if I have a graph, so here's my graph, right, x and y. So if I'm going to reflect it across the x-axis, that means I go from either the top to the bottom or the bottom to the top. Okay. Graphing above the x-axis. Reflection. Okay. How are the equations related? So here is my graph 2x minus 6, and the function g is a reflection of the graph of f across the x-axis. How are their equations related? So graph f, so I reflect every point on f over the x-axis to produce the graph of g by sending every point x comma y on f to x comma negative y. So it's here, it's going to end up here. Okay. So the y-intercept 0, -6, right here, okay, of f is reflected to the y-intercept 0, 6. Okay, so it was here below the x-axis. If I flip it, it's going to come up here. Okay. For any point x, y on the graph of x or f, there is a reflected point x, negative y, or x, negative f of x on the graph of g. So g of x equals negative f of x. So the slope of the graph of f is 2. So that means when I reflect it, the slope of g is going to be -2, the opposite. Okay. So from the graph, you can see that g of x equals -2x plus 6. Here I can reflect it. Okay, so here I see my line. Okay, so here's the original f of x, and here's g of x. So look for relationships. How are the intercepts of a graph affected by reflection across the x-axis? So the intercepts are switched. So if the y coordinate was positive, then it becomes negative, and if the y coordinate was negative, it becomes positive. Okay. So that's something specific to the x-axis. If you're reflecting it, the y is what changes. Okay. So that means if I reflect it across the y-axis, so now I'm reflecting a little graph again. Okay. So here's my y, so it's going this way. X goes this way. Y goes this way. Okay. So, again, I can use, here's my graph. So right now I have an x-intercept right there at 3, 0. Okay, so if I'm reflecting across the y, it would make sense that it would be -3, 0. Okay, so I'm going to go ahead and, so here's my point. I reflect that across the y-axis, which really doesn't change. I reflect x, y, and then I draw my line. Okay. So I picked a point, moved it to the side. Okay. So the slope of the graph here is 2. The slope of this graph is -2. So from the graph, you can see h of x equals -2x minus 6. So we can check that h of x equals f to the negative x by substituting for f negative x. So h of x equals f of negative x. H of x equals 2 negative x minus 6. And h of x does equal -2x minus 6. Okay? So how are the y-intercepts? Okay, how are the intercepts of a graph affected by reflection across the x-axis? We did that one. Okay. All right, so try it. What is the equation for the reflected graph? Check by graphing. So reflect y equals x squared minus 2 across the x-axis. Okay, so remember we're reflecting. Let me go ahead and pull up my calculator. So it's y equals x squared minus 2. So I'm going to go ahead and type that in. Y equals x squared minus 2. Okay, so here is my graph. Now they've asked me to reflect it across the x-axis. So here's the x-axis right here. So I'm just going to reflect it down. So it was, my point was at 0, -2. Now I want it to be at 0, 2. Okay, so in order to do that, y equals negative x squared. So I flipped this. The x squared became negative, and negative 2 became positive. It's a problem. Okay? Because if I were to flip this right here, so if here's the x-axis right here, if I were to flip this, that point would be there. Okay? So for this, y equals negative x squared plus 2. Negative x squared plus 2 across the x-axis. All right, now if I were to do across the y-axis, okay, so the y-axis is here, nothing really is going to change because even if I flip this point, this negative 1.4140 to this side, positive 1.4140, it's already there. And all I'm doing is flipping it across the y-axis. So in this case, it doesn't actually change anything. So this one actually stays the same. Okay, so reflection, y equals x squared minus 2. Nothing actually changed, all right? So basically what happened was when we flipped the parabola across the y-axis, when we reflected it across the y-axis, it was already mirrored, so it didn't actually go anywhere.